Normally at a gathering like this, I'd be giving a talk about field results or laboratory data or vehicle designs. Instead, I'm kind of switching gears here, largely at the advice of NASA headquarters, that we're in a process of the new decadal survey right now, and if we want to advance the agenda for outer planet missions, now is the time to put the ideas out there in the form of white papers. And the topic I'm going to talk about here today has to deal with how we can advance these missions towards flight status. And just to jump a little bit ahead here, for those who don't know me, I worked for a national lab for 24 years and then jumped to a private company back in 2003 when we obtained an A-STEP award back then to look into ideas for autonomous navigation in sub-ice mobility systems. Back then the idea was Europa. That's expanded out today to include all of the ocean worlds. We've built a lot of stuff in the last 18 years, 4 generations of AUVs, 3 of them are under ice vehicles. One of them has just now gone commercial for production. We have worked on a number of cryobot designs. Some of them have been fielded out to glaciers, others tested in the lab under cryovac conditions. We've spent over 400 days on NASA missions alone with these vehicles, either in Antarctica, other remote sites on glaciers, testing out concepts for autonomy for both getting through an ice cap and what you do when you get through it in terms of subsurface ocean. As many of you know from earlier talks today, we're not alone in this pursuit. Many of the people in this room also build hardware in addition to pursuing science and theoretical aspects of the possibilities for life and where that might be in the ice. And so that brings us down to an issue of how does this all work? For people who have been around long enough, there was an organization called TriWig back in the 90s, which was advancing what they then called teleop systems, but really it was looking at ideas for mobile autonomous systems and how those might be used for future planetary missions. That kind of evolved into a more complex program with A-STEP, looking at combining both scientific aspects of a mission, that is science payloads on mobile robotic systems and using those in analog environments. And now the current acronym is PSTAR. I'm sure that many of the people in this room have been funded by that organization. The problem is, and as everybody knows, it's a big group out there that's competing over limited funds, and they tend to focus their work at a site where it seems to be convenient to test out that singular concept. There doesn't seem to be a lot of cross-sharing of ideas in terms of where would be the best place to test some of this out that might be able to pool resources and thus get more work done in the field. This is not the case when you jump over to the human side of exploration within NASA. Over the last 2 decades, NASA has spent probably $1 billion plus in dollars in analog environments, not just limited to things like the Sonny Carter Neutral Buoyancy Lab, for those who have been out there, the world's biggest indoor swimming pool, and ongoing work, for example, at the NEMO facility off the south coast of Florida, where astronauts are still trained today. So the idea of analog environments is not new to NASA. The trick is, how do you focus the political will and the community to get behind that to come up with a place where you can logically move things to the next technological level. There was a meeting a year and a half ago out at Caltech looking at concepts for getting through the ice cap. And that's the first time that I remember there being a discussion of the idea that there might be a general need for a site that would be a test site for all outer planet systems that might be looking for subsurface access. And in that sense, we're talking about not only the lander deploying a device that goes through the ice, but then the device that goes through the ice either doing something below that ice cap or deploying a sub-payload mobility system that would continue exploration to a further radius out there. So here's hopefully this will play here. This is something we put together with National Geographic a couple years ago, and it's kind of like 40 seconds of how to do this mission. Let's see if it'll go. There we go. I've removed the sound. It's a little too dramatic. But the idea is you land, you get through the ice cap starting with a temperature of about 77 Kelvin and hard vacuum. You avoid any type of debris, cracks, voids, water on the way down. When you get to the bottom, you break through, you deploy some sort of mobility system, and then off you go into a planet scale ocean looking for something that might be an energy source that might provide a better opportunity for finding life. And then you phone home. So nothing hard there. So let's just break this down for a second. When you start to look at the regimes that you have to work with here, okay, and I'm not talking about the folks who are out there looking at Dragonfly missions to Titan and things like that. Those are surface missions, right? We're talking about the next step beyond that. How do you go subsurface in whatever planet you're really interested in? So in most cases, you're looking at a lander deploying some type of a vehicle into the ice. Now, when you look at that problem, you find out that it's not as trivial as you might think. So how do you test all of your ideas for getting from the lander into a piece of ice that may or may not have some type of impurities in it, whether endogenous or exogenous of origin, and then getting to a point where you have actual water forming below the vehicle? That's not going to happen at the surface because everything sublimates into vacuum, and you've got ice as hard as concrete is the one analog I've been led to believe. So you have to create that environment in the lab, and there's a bunch of problems with that. This is a tank that we've built over the last year at our shop down in Austin, and it's powered by about 10,000 liters of liquid nitrogen and 3 stages of vacuum systems, just so that you can put an object in there. Now, all of the thermal analyses that we've done indicate that these things have a limitation on what you can put in there. So this facility can be rightly considered a scale model test lab. If you work it out for a cryobot, which has a diameter and a length, if you want to avoid boundary conditions affecting the results of the tests, you need a chamber that is at least 10 vehicle diameters in diameter, more like 20 to be safe. And you're looking at about 5 to 8 vehicle lengths in order to be able to look at cruise phase behavior of that vehicle. And so that gets to be a fairly big facility, if you will, kind of like on the scale of the Sonny Carter neutral buoyancy laboratory. It doesn't exist. Right now, as far as I'm aware, this is the only dedicated cryovac facility that has a column of ice in there for the purpose of testing cryobots. I don't know if this is going to play here, but I'll just see if we can, hopefully this will go. This is a test that was conducted just last January, and it is a laser-powered probe going down. It's about 3.5 centimeters in diameter, about 15 centimeters long, and the thing that's important to know here is a lot of the predictions for this kind of stuff indicated that it would just stall in the surface. It turns out that if you have the right energy configuration along the sides, it'll go. We were actually able to make a passive probe go into this with the right thermal profile down the side. So a little thermal modeling goes a long way. Once you get in, the important part, I don't know if you watched the last bit there, just the last few seconds, this is all sped up by a factor of about 50. The actual test is about 25 minutes long. We were running about 600 watts of laser power into the probe. But the ice sublimates directly to gas. When it comes out, it hits the surface, it sublimates or freezes back down. It forms a little cone of snow around the outside, and eventually it begins to freeze the hole shut. And so it's at that point that you have to start thinking about, all right, how does the vehicle move forward through ice? How are you going to get it through the brittle phase? So there's a whole bunch of issues here, right? These phases we talked about. There are things that you can do only in the lab, and that's those first two, the starting up phase and then cruising through brittle ice. But other things actually require an analog test site. One is obstacle avoidance. For example, if you hit a crack in the ice, you hit a void in the ice with water, liquid water in it, or something that would just be a gaseous void. These are things that are problematic. Not so much the presence of a giant piece of asteroidal material, but more like voids. What do you do when you break through? How do you control your vehicle? Because if you just drop into something, that could be a mission terminating event. How do you go through ductile ice for long periods of time? For those who have been involved with this, the discussion points right now indicate a mission time of 2 years to get through a 20-kilometer ice cap with a small radiothermal source or a fission source. When you get to that breakthrough point, how are you going to control the vehicle, and do you look only at the ice-water interface, or do you drop all the way to the ocean floor and then radially explore out to there? The final stage of these things involves enhancing your mission radius by exploring out from the point where the cryobot drops you in. The likelihood that your cryobot is going to land directly on a hydrothermal vent seems pretty low. So eventually what we're going to find here is that all of the people who are working on these various pieces of equipment are going to start converging on a common theme, and that is, if we want to really prove this stuff out through TRL-6, bringing us up towards flight stage, we need a place where we got kilometers of ice. We're going to be breaking into some type of subglacial water body, whether you believe this should be an ice shelf or an ice sheet, and when you're going to a static subglacial lake or an extension of something like the Ross Ice Shelf in the ocean underneath, you're still going to need a common logistics hub to be out there on a regular basis and long duration mission support. This is something that doesn't happen right now. Everything goes out on a yearly basis. Everybody puts temporary camps in and you get your data and you come home. You can't do that if you want to try a true mission simulation for something like Europa or Enceladus. These are things are tractable, okay? Where are the places? Well, the obvious one is Antarctica. There are subglacial lakes registered in Greenland. There are a few elsewhere, for example, in Iceland. The question is, which of these makes logistical sense for a focused US program in this area? And right now, getting a consensus on that is something that we're trying to do. The decadal survey is around, and I've been encouraged to try to get as much participation from the community in this as possible. And that's not just the hardware designers and the software coders. It's all of the scientific community that might think, all right, if we're going to go do this as a joint effort, in which, for example, we have multiple cryobots supporting multiple missions to see which of these is going to survive. How many people here think that a vehicle that you design in your lab is going to work when you take it to Antarctica for the first time? Put your hand up. All right, an optimist. No, the whole idea about this is to break them, okay? And Antarctica is awesome for breaking things. You can ask anybody who's been there. But that's how you learn. That's how you learn. And, you know, the logic that I remember a long time ago from Peter Doran when we first went down was that you really need 2 or 3 seasons to shake something down to production science. The first one, you're going to utterly fail. The second one, you're bootstrapping and learning on the fly. And the third one, that's when you get the killer data. So we have to do the same thing for this kind of stuff. You can't simulate this in a lab. You need something that is going to get you a long time in the field, putting the crews who are going to run these vehicles out there with it. So the idea of a year-long mission in Antarctica to do a Europa simulation is not out of the question here. We have to start thinking big, right? And we need a place where everybody can go and test together. not just one group here, one group there. It just makes a lot more sense to pool these, and if you put it near something that is already an existing logistics hub, let's say, for example, South Pole Station or Concordia Station, things of that nature, then you have a way to put the crews out there and start doing this on a routine basis. And then what we're hearing every year at conferences is, hey, this worked, that broke, here's what we're doing to fix it, and here's the results of this mission. And this is what's happening to these vehicles that are down there for a year. You know, are they going to survive that long? Or is there corrosion problems? Are there material problems? Is there biofouling? Well, that'd be a great thing to have on Europa. But and so the idea is, yeah, kind of coalescing here. These are the main things we're looking at. A place to test ice penetrating vehicles in kilometers thick ice, to be able to deploy autonomous underwater vehicles either by those cryobots or initially simply downhole to get long duration testing on them, testing of multiple technology approaches in parallel, dress rehearsals for planetary protection measures, and that is to say pre-sterilization of vehicles, not the procedures that are currently used, for example, that involve dramatic logistics for filtering water, and year-round operations. And so what we're doing right now is working with headquarters and LPI to come up with a final site and date. It's probably going to be sometime after October 15th this year. Those who would be interested in putting some feedback and information into that and participating, feel free to contact me. But this is something we're trying to move along with the idea of having a white paper for the National Academy submission sometime early next year. So that's it. Thanks.
Yeah, great talk, Bill. Is this something that could be done collaboratively with the earth science community that's doing the deep drilling, or would this be something quite separate from that?
When you say deep drilling, you're talking about RAID or
ice coring and things like that. Is it something you could have the same station, or would it need to be
the answer is yeah, sure. Most of those guys, though, are single season grants, if you will. Well, SALSA was like two. And so if they had a site that they were willing to work at, you could use the same equipment. You can use a hot water drill to provide access. Brittany can tell you about that. So to me, it's not a question of whose equipment are you going to use. It's how do we make it a sustaining thing. So it's not just one shot and then there's a 3 or 4 year gap while people are struggling again to get another proposal into NSF or NASA. The idea is to get Congress behind this to where they say, you know what, this is a national mission. Let's make this important. It's a 10-year or whatever continuing effort. It's a facility that is supported, just like, for example, some of the NSF long duration sites like Waste Divide, AGAP, and things like that. So if we use those same facilities, okay, if we use the RAID drill or if we use a SALSA drill, it doesn't matter to me. Those are fine for early access for some of the science payloads. In parallel with that, you have new technologies that are actually going to supplant things like those classical drilling technologies. Cryobots are self-contained devices that do the same job, and they are not constrained by the time limits that you get, for example, with a hot water drill. You turn off the drill, you've got about 36 hours before the hole is far too closed to put down a skinny type vehicle or an ice fin type vehicle. So in this case here, the cryobot does the transport, it goes down, it stays there for several months. You then bring it back up when you're ready. You reverse melt on the way back up. This is a totally different methodology from what we've been using so far.